Welcome back. In this video, we will learn work, energy and power. We will understand the key concepts, important formulas and real life examples in simple and easy way. So let's get started. Before we begin, let's understand why this chapter is so important. Have you ever wondered how a person lifts a heavy box? Why a car speeds up when you press the accelerator? How a crane lifts massive concrete block? Or why a football travels so fast after being kicked? All these everyday activities involve the concept of work, energy and power. By understanding this chapter, you will learn how forces make objects move, how energy is transferred from one form to another form, and how power tells us how quickly work is done. These concepts are not only important in your exams but also important for engineering, sports, transportation, and many real life applications. Let's start with the first concept, work. Work is done when force acting on an object causes it to move or produces displacement. Look at the first picture. The person is pushing the box but it doesn't move. Since there is no displacement, no work is done. Now look at the second picture. The box moves forward when the force is applied. Here both force and displacement are present, so work is done. Remember, force alone is not enough. Work is done only when there is a displacement. Let's look at the formula. Work equals force multiplied by displacement multiplied by cosine of the angle between them. Here W represents work, F is the applied force, S is the displacement, and theta is the angle between the force and the direction of displacement. The SI unit of work is the joule, represented by the J. There are three types of work: positive work, negative work, and zero work. These depend on the direction of force with respect to the displacement of the object. Let's understand each one with the examples. Positive work is done when the force and displacement are in the same direction. In this example, the person is pulling the trolley forward and the trolley also moves in forward. Since both the force and displacement are in the same direction, the work done is positive. Here the angle between the force and displacement is 0 degree. Negative work is done when the force and the displacement are in opposite directions. In this example, the car is moving forward, but when brakes are applied, the brake force acts in backward direction. Since the force opposes the motion, the work done is negative. Here, the angle between the force and displacement is 180 degree. Zero work is done when the force is perpendicular to the displacement. In this example, the person is walking forward while carrying the suitcase. The displacement is in forward direction, but the force applied to the support suitcase is upward. Since the angle between the force and displacement is 90 degree, the work done is 0. Let's solve a simple numerical based on the work formula. A box is pushed with the force of 10 newtons and moves 5 meters in the same direction. Since the force and displacement are in the same direction, the angle theta is 0 degree. Using the formula of work is equal to force into displacement into cos theta, we get work is equal to 10 into 5 into cos of 0 degree. Since cos 0 equals 1, the answer is 50 joules. Therefore, work done is 50 joules. Energy is capacity to do the work. Any object that can perform work possesses energy. In this example, the battery stores electrical energy. When the circuit is connected, energy flows through the wire and lights the bulb. The SI unit of energy is the joule and represented by capital J. In this chapter, we mainly study mechanical energy, which has two forms, kinetic energy and potential energy. Kinetic energy is related to motion, while potential energy depends on the position of an object. Now, let's understand mechanical energy. Mechanical energy is the energy possessed by the body due to motion and position. In simple words, it is the sum of kinetic energy and potential energy. A roller coaster is a perfect example because as it moves, it continuously has both kinetic energy and potential energy. Look at the roller coaster at the top of the track. Since it is at the greater height, it has the maximum potential energy. At this point, its speed is very low, so its kinetic energy is minimum. As the roller coaster moves downward, its potential energy changes into kinetic energy. At the bottom of the track, its speed is maximum. Therefore, kinetic energy is maximum while potential energy is minimum. Throughout the motion, the roller coaster always has mechanical energy. Kinetic energy is the energy possessed by the body by virtue of its motion. In this example, the football is moving along the road. Because it is in motion, it has a kinetic energy. The faster an object moves, the greater the kinetic energy. Potential energy is the energy possessed by a body by virtue of its position or configuration. This power plot is hanging at a height above the ground. Because of its position, it has a gravitational potential energy. The greater the height, the greater the potential energy. If the pod falls, this stored potential energy changes into kinetic energy. Let's understand the transformation of energy. Transformation of energy means energy changes from one form to another form. In this example, the coconut is hanging on the tree. It has a potential energy because of its height. As it falls, its potential energy gradually changes into kinetic energy. This is a simple example of transformation of energy. Let's understand the law of conservation of energy. Energy can neither be created nor be destroyed. It can only be transferred from one form to another form. Look at the child on the swing. At the highest point, the child has maximum potential energy. As the swing moves downward, potential energy changes into kinetic energy. Although the forms of energy keep changing, the total mechanical energy remains constant. Now, let's understand work energy theorem. It states that the work done by the net force acting on an object is equal to the change in its kinetic energy. Let's understand this with a simple example. When the player kicks the football, a force acts on the ball and work is done. As a result, the ball starts moving and gains its kinetic energy. This shows the work done on the ball is equal to the increase in its kinetic energy, which is the work energy theorem. Now, let's understand power. Power is defined as rate at which work is done or energy is transferred. In this example, the worker lifts the box from the ground and places it on the table. If the same work is done in less time, more power is required. So power tells us how quickly work is done. The power is calculated by dividing work done by its time taken. The formula is power equals work divided by time. Here P represents power, W represents work done, and T is the time taken. The SI unit of power is the watt and represented by the capital W. Power can also be calculated using the formula power equals force multiplied by its velocity. Here P represents the power, F is the applied force, and V is the velocity of the object. This formula is used when force and the velocity are known. There are two formulas of the power. Use P is equal to W divided by T when work done and time taken is given. Use P is equal to force into velocity when the force and the velocity are known. Choose the formula based on the information provided in the question. Forces are mainly classified into two types: conservative forces and non-conservative forces. Conservative forces conserve mechanical energy. Common examples are gravity and spring force. Non-conservative forces do not conserve mechanical energy. Some energy is converted into heat or sound. Common examples are friction and air resistance. In this example, the ball is thrown upward. As it moves through the air resistance, which is a type of friction, acts opposite to its motion and slows it down.